Now, I'm just going to record the session. Okay. Now, I'm going to continue with 20 to 25 minutes. Let me just go over it. I think it's a cockroach over there. It feels like a cockroach. No, but it's not. Don't worry. Now, okay. Everyone's ready now? Okay. Today is going to be our discussion. Before we just go for the midterm, for the final things on the matrix algebra, which I'm going to say that, guys, I'm going to give you a matrix, okay, which this matrix can have any kind of rankings. For example, it can be m times n, which, as you remember, it means that the matrix which we have has m number of the rows, n number of the columns. Then what we do is this, that I'm just going to factor it in two matrix. For example, what happened? Look at what happened. We just do that. Are you? It's not a very hard topic. Don't be afraid. It's okay. Huh? Then the thing that we do that, for example, like the factorization, what we did before, we say number 6, for example, you factor it into 3 and 2. You say 2 times 3 becomes 6. That was a factorization we did with the integer numbers. We did it maybe in elementary school. Now, what we do, we are just going to do the same thing. Okay, we are going to do the same thing for the matrices. However, today, when you submit your workshop, you have to also submit a one paragraph to say that. For example, if you have a matrix of the gene expressions, everyone knows about the gene expressions, huh? From the biology and the genome sequencing that you have learned, you're going to come with one paragraph when you submit your workshop. And that's going to be the thing that you do yourself, that if you factorize the matrix of the gene expressions by the method which I'm just going to show you, what is the interpretation of each matrix that you get from the factorizing that gene expression matrix. For example, you have a cancerous tumor, you sequence that gene using the Illumini methods that you learn in either biology 1 or biology 2. Then you have the gene, you have the readings of the gene expressions. Then you factorize it with this method, what each matrix may represent, and just simple one paragraph. Do not go too much deep in there, okay? And that becomes part of the thing that when you copy paste the workshop from here, you add it at the end before you submit it. Sounds good to everyone? Oh, look at her. She's so excited, huh? Now, I said that we have a matrix A, m row, and n columns. I'm going to factorize it. Means I'm just going to build two matrices. I'm just going to call the first one Q, which I make sure that this is a square matrix, which it comes as m by m. You see, it means that it's a square. It has m number of the rows and m number of the columns, which is multiplied to another matrix. Yes, please come in. Which is multiplied by another matrix, which is now, I have a little bit difficulty to form it. Guys, now look at that. In order to identify this matrix, look at that. We have the two matrices that they are multiplied. Okay. Oh, brother, look at that. Why there? Please come front. It's become too compact. Come to the front. Yes. Yeah, thank you. You see, it's so, oh my God, it becomes so packed. Now, then the next matrix that I'm just going to build, the characteristic, what is that going to be? Because I know that this one has to be compatible for multiplication. Then I have m number of the columns here. The matrix R has to have m number of the rows. And because I have n here, number of the columns of the resulting matrix, I know that n has to be here. That's the thing that you learn, how to make two matrices compatible when you are just multiplying together, that indices should match in that way from last week. Now, the matrix Q that we are going to build today, because we are going to start with the matrix A, which is given, we are going to build matrix Q, which is orthogonal matrix. We learned it last week. We said that orthogonal matrix is that if you have a matrix which is orthogonal, you remember from last week, I say if A and B are orthogonal, A multiplies B, it gives you an identity matrix. It was a very important thing that we learned last week. I'm going to review that here, that when we say matrix Q as a result of factorization, this is very important when you come to write your interpretation of factorizing a gene expression matrix into Q and R, because Q has to be orthogonal. Okay? Q has to be orthogonal. That's right. This is an orthogonal matrix. It is very important when you write your interpretation. Orthogonal, and R is a matrix which is upper matrix. We're going to talk about the upper matrix in a couple of seconds. However, I'm just going to review of again what is the roadmap. Then what we are going to do here is this. We are start with a matrix. It can be the gene expressions of a cancerous tumor. It comes with n number of the rows and n number of the columns. We are just going to factor it into two matrices that when they multiply together, like 3 and 2 gives you 6. This is the real matrix. The first matrix is a square, comes with n number of the rows, n number of the columns. This is an orthogonal matrix, which it means that if you remember, orthogonal matrix, we said that this has a very important quality, that their inverse is equal to their transpose. It was just a very important characteristic of orthogonal matrix. We discussed it last week, and you're going to use that orthogonality when you just come with the interpretation. And also R, we said that that's an upper matrix. Upper matrix is what? I'm just going to read it very quickly before we just go for one example. We say, for example, R comes into this format. We said that R, we said that you can have your diagonals. Diagonals are elements which are standing at the same row and the same columns. Row number 1, column number 1. Row number 2, column number 2. We say all the elements upper. We call it upper triangle matrix. We said that, look at that. The form which I have upper the diagonal, it's a triangle, huh? And I have a triangle at the bottom. I said that the triangle upper the diagonal, they have any other numbers. For example, 1, 2, 4, 6, any numbers. But the lower diagonal, everything becomes 0, 0, 0, 0, 0. This matrix becomes very important in the significance that it plays. We call that upper triangle matrix. Means that if you draw a diagonal, the triangle which you form on the upper part of the diagonal, it comes everything non-zero. The diagonal in the lower part of the diagonal, the triangle lower part of the diagonal, everything becomes 0. And that becomes the R. Then what we are going to do right now is that I'm going to give you an example of the matrix. You factor it into two matrices. One orthogonal matrix, one right upper triangle matrix. This is a very important thing in the application that you're just going to talk about that in one paragraph. Now, these were blah, 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 which we did. Now, essentially what we do is that I'm just going to go next page to build the structures of the first example before we just go for the next break. The matrix which I'm just going to start with it's a matrix which has 3 number of the rows and 2 number of the columns. This is the characteristic of the matrix. As an example, I'm just going to do. What does it mean? It means that, for example, the rows, I have row number 1, row number 2, row number 3. Columns, I have column number 1, column number 2. That forms a matrix which is 3 by 2. Now, I'm just going to fill out the numbers in there. For row number 1, column number 1, it's going to be a +1 number. For row number 2, column number 1, again, is going to be a +1 number. For row number 3, column number 1, it again is going to be a +1 number. Now, I just go to the column 2. For row number 1, column number 2, I assign it to be +1. For row number 2, column number 2, I'm going to assign it to be 0. For row number 3, column number 2, I'm just going to say the number there, it becomes -1. Then as you can see, I form a matrix, which is 3 by 2, comes with 3 number of the rows, 2 number of the columns in that format. Now, what we become interested is this. We say that, can we do this? Can I build this matrix? Matrix A, which is 3 by 2, can it be formed in that way? Can I make a matrix which is going to be Q? Matrix Q times matrix R. That's what we are just going to do today. Okay, I'm just going to decompose it in these two ones. Now, it takes only 2 steps. I'm just going to follow these steps very quickly. I'm just going to say step number 1. Step number 1, we just attack matrix Q. We just say to find matrix Q. In order to find the matrix Q, we have one very simple strategy. I'm just going to do that. And also step number 2 is going to be find matrix R. In order to find matrix Q, I'm just going to start with this strategy. I'm just going to define, look at the first column which I have over here. Everyone sees that? I'm highlighting it. I'm going to call this one column 1. And I'm going to build a vector out of it. What does it mean? Look at that. I'm just going to imagine this is a cake. You go with the knife to cut that piece of the cake. If you do that, you see that you have +1, +1, +1. Okay? Now, but the cake needs a container, which is a plate. I'm just going to put that inside to form a vector, a column vector. I'm just going to call that what? A1. I'm just going to call that A1. Now, this is the first thing which I'm going to do. The second thing which I'm going to do is this. I said that when I build this vector, I'm going to put this number 1, step number 1 here. When I build this vector, everyone remembers from maybe high school that if you had a vector, for example, if you had a vector like this, let me change the color. If you had a vector like this, for example, V was a vector like that, A, B, C. It was a vector in space. You just wanted to find the norm of this vector. The norm of this vector was what? Look at that. This is two parallel lines on each side of the V, which it means that you're just going to find the length of this vector, which we call that the norm, was essentially what? Was this one. A squared plus B squared plus C squared. For example, if you had a vector 1, 2, 3, was 1 plus 4 becomes 5, plus 9 becomes 14, square root of 14. That's how you find the norm of a vector. In the step number 2, which I'm going to do here, is this. I'm just going to go, okay, I'm just going to find the norm of this vector. I'm going to say part 2. I'm just going to, the vector A1, which I got, I'm just going to find its norm. Its norm becomes what? Like this formula, which I said, becomes 1 to the power 2 plus 1 to the power 2 plus 1 to the power 2, which becomes essentially square root of 3. Anyone's taking notes? Yes? Awesome. Now, then what did I do so far? The first step was that I choose column 1 of that matrix to call it A1. I found its norm in step number 2, and in step number 3, that's what we call normalization. You're going to hear about that word many times, even if you just go to get the job. Normalization. What the normalization means is that the vector that you built, which was A1, you divide it by its length, which is length of the A1. Okay, means that you got a vector, you divide it by its length. Then I'm just going to call that Q1, which stands, we do not go too much deep on the abbreviation. I'm going to call it Q1, which it means that what is 1 over the length, which is 1 over square root of 3, times A1. What is A1? This is this vector which we had, plus 1, plus 1, plus 1. And this is all that we need to do for this stage. Then, in order to factorize this matrix, what did I do was this one, that I just selected one column. I normalized it by dividing that into its norm or its length, which we got Q1. And I'm just going to highlight Q1 with a cool color here because it becomes what we are going to use before. And I'm just going to call Q1. Let's call it equation. I'm going to write equation number 1, which is a very important one that we need. Okay. Now, I just go to, we had how many numbers here so far? We had number 3. I'm just going to go to number 4. For number 4, what we are going to do is this. You say, okay, I'm going to ask you, for example, what you guess for part number 2. How much we have taught so far? 15 minutes or more? 15? Okay, then I'm just going to finish it with A2, then we take a quick break, huh? Yes? We should be on time then. Now, then at this stage, you say, okay, what I did so far, it was I selected column number 1. I normalized it. Then you expect that what I'm going to do, step number 2, is that I'm just going to select column number 2 to normalize it. You say, for example, column number 2 is going to be this in this initial matrix, and I'm just going to do the same thing. Say A2 equals a vector column of plus 1, 0, minus 1, normalize it like that way. This one comes with a little bit trick, and the trick is that you have to do this one. And this becomes a very important thing. I hope that you take notes in the workshop that you're going to submit. That A2 becomes, I'm going to call that A2 prime, becomes the A2 itself, the vector 2, which I showed over there, minus the projection of A2 along Q1. I'm just going to specify what do we mean by that. This is a very important thing. For example, if our matrix had the third column, we have to do this one. We make the projections of A3 along the Q2, which you're going to see what do I mean. This is a very important equation. I'm just going to put the star next to that. Now, in order to find the projection, then I'm just going to write A2 here. A2. A2 for us, which comes from this equation, is this. A2 becomes this matrix, which it was what? Which it was +1, 0, and -1. This is the matrix A2. This is the column A2. But I do not know, I should not jump into normalize it because I have to subtract the projections of the A2 along the Q1, which I got. Now, in order to find the projection, it has a very interesting geometric interpretation. I'm just going to share that next week when we come back after the midterm. But here, I'm just going to give you the formula. We say that the projection of A2 along the Q1, which is a normalized A1, it becomes this equation that it becomes A2, the vector which I have, dot Q1, let's use Q1 dot Q1 times Q1. Okay, that's a projection. Write this formula the way which it is. The answer, why is that so? Because of the geometric interpretation which it adopts. I'm going to talk about that after the break. Okay. Now, we said that if we have, for example, we have the A2 here, which is the column vector from the original matrix which I have. I said that the projections of the A2 along the Q1 which I got, which is the normalized vector, is this expression. This is a dot product. Now, I'm just going to do this one here. Then we see what do we have. I'm just going to finish with this projection. Then I'm just going to stop for a break. Then we come back to continue with the rest of it. Sounds good, everyone? Yes? Now, okay, in order to do so, we have a dot products of two matrices. What does it mean? Let me write everything that we had. I'm just going to find this one. I'm just going to focus on this one. A2 dot Q1. Look at it. There's a trick over there. Not you, actually. I looked that way. Okay, what is A2 here? We have +1, 0, -1. Which is, what is the ranking of this matrix? What is the ranking of this matrix? It has 3 rows, 1 column. 3 by 1. I'm going to write the Q1. What is a Q1 we got? It was the square root of 1 over square root of 3 into the matrix 1, 1. I'm just going to write it like that. 1, 1, 1. We had it multiplied to 1 over square root of 3, which is also again 3 by 1 matrix. And now, before we go for the break, you ask yourself, there's a problem. I cannot multiply these two matrices because they are not compatible. Why is not so? Because look at that. Look at this. I have 1 here and I have 3 here. Remember from last week, we said that in order to multiply two matrices, they have to be equal. But they are not. We have to make them equal. In order to make them equal, look at this one. They are not. This is 1, there is 3. There's a problem. But imagine that if the matrix which I have here as A2 instead was 3 by 1, it was 1 by 3. If it was 1 by 3, I had 3 and 3 equal. Then they were compatible for multiplication. Then as a result, we come to give this very interesting property. And I say, if I were multiplying A2 transpose, A2 transpose, you remember we said that we changed the number of the columns by the number of the rows. Then A2 transpose, what is the ranking of it? Becomes 1 by 3 matrix because you swap the columns with the rows. Then 3 by 3 becomes similar. Then as a result, in order to find a projection, for the projection, I'm going to do this. I'm going to say for the projection, I'm going to multiply A2 transpose times Q1. Then what happens? A2 transpose. A2 transpose, what did we have? A2 was, look at that, A2 was this matrix, which we had plus 1, 0, minus 1. A2 transpose becomes what? It is 3 by 1, becomes plus 1, 0, minus 1, which is 1 row, 3 columns. Now, then as a result, if I go back up there, the A2 transpose becomes this format. Plus 1, 0, minus 1, times Q1. Q1 is what? Plus 1, plus 1, plus 1, which I know this is also multiplied that to 1 is root of 3. I know this one is equally distributed to all elements of the Q1. Then I'm just going to multiply that. Then in that case, let's see what happens. We have 1 by 3. Look at that. The ranking is 1 by 3. This one is 3 by 1. Remember what we discussed before. We said that now they are compatible because 3 here, it makes that these two become compatible for multiplication. And this one here, these two form the resulting ranking of the matrix, which means that it becomes a matrix which is 1 by 1. What is a matrix which has element 1 by 1? It means that it has 1 row, 1 column. It is only one number. That's right. In order to find the answer, I'm just going to write it here, which it means that this one becomes this. I'm going to multiply this one to this one. 1 times 1 plus multiply this one to this one. 0 times 1 plus multiply this one to this one plus minus 1 times 1. How much do you get at the end? This one becomes 1. This one becomes 0. This one becomes minus 1. Plus 1 plus 0 minus 1 gives you how much? 0. Then, look at that. What happened? We got A2 transpose times Q1, which is essentially, if I go to this previous page, which is essentially this one. Look at that, A2 transpose Q1, which is the numerator of the projections of A2 along Q1 is 0. 0 over denominator becomes 0. 0 times something becomes 0. Then it means that the projection of A2 along Q1 becomes how much? 0. Then this term, the second term here, becomes how much? 0. Then A2 prime, in this case, becomes A2 itself, because the projection along that becomes 0. Now, we are just going to take a quick look. Okay? Now, I'm just going to go ahead with the... Guys, please quiet. This is a perfect place. Please come here. No worries. Come here. I can see such a beautiful place. Now, okay, now, for the last part, the thing that we are just going to do today is that before we just went for the break, I hope you took notes all the way up to here. We said that, okay, we just started with the vector A1. We normalized it. We just derived Q1. We just went for the vector A2, which is the second column of the given matrix as an example that I was solving that for you. We said that, okay, when we just have the A2 as a second column, as a second vector, we do not just normalize it. We just first have to find the projections of the A2 along the Q1 which we had, then subtract A2 from it, then we normalize it. Then if the matrix that we have, it has the third column, then we had to go for the third column. Then we make a projections on the Q2, then subtract A3 from it to get the component from there. Now we have only the second column, then we just do the second step that we had. Then you remember from before we just went for the break, we find that the projections of the A2, which is the column 2 of the given matrix, along the Q1 becomes 0. Then when you subtract A2 from that projections, you get back the A2 itself. This is one exception. This is a very particular case here that you do not, you have the projection 0, and you have to just go right away with the A2. Then the thing which I'm just going to do is this. Then instead of writing, let's say, A2, then you remember we said that A2, I just called it the prime, becomes A2 itself, which is the second vector from the second column of the given matrix minus the projection of A2 along the Q1. You saw that this element, this part, just went to 0. Then the only thing that we had then the A2 projected one is the initial A2 that we had. And remember, we had A2 as what? We had A2 from the given matrix as +1, 0, and -1, which is exactly the second column of a given matrix. Now, what we have right now is that we have to normalize it as what I did with the A1. In order to normalize it, I have to find the norm of the A2. The norm or the length of the A2, from what I discussed before the break, it becomes +1 squared plus 0 squared plus -1 squared. Then you add everything together, you get square root of 2. Then noticeably, then what do we have here? Then if I want to normalize A2, I'm just going to call that Q2, which it becomes the A2 matrix itself over the norm of the A2. You can double check it. You get the norm of the Q2 becomes 1. That's why you call it, you have normalized it. Then 1 over norm of A2 becomes 1 over square root of 2, multiplies to A2. What is A2 here? We have +1, we have 0, we have -1. Then now, I'm just going to go to the next page. Then what did it so far? From the given matrix that I was given as a matrix, which it was 3 by 2, the matrix which was given as 3 by 2, which it was given as +1, +1, +1, +1 here, the second column, 0, and -1. From this matrix, I obtained the sets of 2 orthogonal and normalized vectors Q1 and Q2, which you are able to expand the space as the matrix A. However, in order to form it, I'm just going to call this one, this Q1 and Q2, which I found, they are just going to form the matrix Q. Why am I doing that? Because remember, I said that the matrix A, which I started here, becomes, did I finish 25 minutes? You were signaling. Oh, I thought that the time flies so fast. A becomes Q times R. You remember that's the main formula that we're looking for to factorize this into this format. Now, the Q1 and the Q2 from this method which I discussed so far, it builds the Q matrix. Then I'm just going to write it. Look at that. What we had Q1. Q1 was the square root of 1 over square root of 3 over plus 1 plus 1 plus 1. Q2 was 1 over square root of 2 over plus 1, 0 minus 1. Then, as a result, the matrix Q, which I'm just going to put these two matrices together. What does it mean? Q1 becomes the first column of the matrix. Remember, Q1 is the normalized one of the column A1. Then I'm just going to put it there. I'm going to take 1 over square root of 3 inside this. Then I get plus 1 over 1 square root of 3 plus 1 over 1 square root of 3. And also plus 1 over 1 square root of 3. Now I'm just going to go to the second column. The second column comes from where? The second column is essentially Q2 corresponds to the A2, which I had here. Then I just put it there. I expand 1 over the square root of 2 inside this, becomes plus 1 over 1, 2, becomes 0. Exactly. Absolutely. And now this matrix, which is a 3 by 2 itself, now becomes the Q matrix, which I find it here, it is orthogonal. This matrix is orthogonal one, forms the Q matrix. Now, you see that the step number 1 that I targeted to find matrix Q is done. Sounds good? Now, the next step which I'm going to do, everyone's okay? Everyone has written that? Should I go to the next? Okay, the next thing which I'm going to do, the me brother, come to sit over there. I'm going to see more of you. Come over there. Don't be shy. Don't be shy. No, don't become that aggressive. No, look at that. What did it so far? No what? Okay, what I'm going to do right now, I expanded the matrix. I was given the A matrix with all the things, blah, 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 which I talked about. We were able to find the matrix Q, which is an orthogonal matrix, which, as what we learned from last week, its transpose is equal its inverse. Now, what I'm going to do right now is that, what was the purpose? We said A should be equals to QR. I find Q, I was given the A, then I'm just going to find R. For example, imagine you are given 6 equals, you're just going to factorize 6. You get 3x. What is x? 2. X means what? Huh?
Explain fast.
Yeah, x means what? 2. Then how did I get that? I divided both sides by 3. I'm going to do the same thing. I'm going to divide. Look at that. If I'm looking for the matrix R, I'm just going to divide both sides by Q. To get the matrix R. Then as a result, R becomes A divided by Q. Does it make sense? Now, but they are the matrices. You cannot find them like that. Then what I do, I just R equals Q minus 1 over times A. That's right. For example, if you had here, for example, for this case, as I wrote equally, X becomes 6 over 3, which gives you 2, or essentially I can write 3 to the power minus 1 times 6. 3 to the power minus 1 is the inverse, huh? However, guys, you remember from last week, and also what I discussed today is that we said that Q is an orthogonal matrix. Orthogonal matrix that has this important property, that the inverse of an orthogonal matrix, it should be equal to its transpose. It's a very important thing because we do not have to just go to a laborious things to find the inverse of that matrix. We have to find the determinants. It has many things to do. We only transpose it, we get the inverse of that. This is a very important thing we discussed last week. Then as a result, the matrix R, which is going to be the upper triangular matrix, becomes what? Exactly inverse of the Q times given matrix A, which is so important. Now, I'm just going to put everything there. I'm just going to write QT here. Look at that. Q was the matrix which I got on the previous page, was 1 over square root of 3, 1 over square root of 3, 1 over square root of 3, 1 over square root of 2, 0, minus 1 over square root of 2, right? However, now I see that I do not need the Q itself in order to get the R. I need the transpose. QT. Q was a 3 by 2 matrix. QT becomes 2 by 3 matrix. It means that now the first column becomes the first row. What is the first column? This one. You put it as a row. 1 over square root of 3, 1 over square root of 3, 1 over square root of 3. What is the second column now? Second column is this. Becomes now the second row. 1 over square root of 2, 0, minus 1 over square root of 2, which now becomes a 2 by 3 matrix. Sounds good so far? Now, what I'm going to do right now is to find the R by multiplying Q transpose, which is this matrix, which I got. Into matrix A. What was matrix A? Plus 1, plus 1, plus 1. Minus plus 1, 0, minus 1. Look at that. Now, the first question is that, are these two matrices compatible for multiplication? The first matrix ranking is what? 2 times by 3. This one is what? 3 by 2, right? Then you see that the 3 which I have here matches this 3, means that these two matrices are compatible. What is the ranking of the resulting matrix? The resulting matrix comes by the ones which are left. Exactly, 2 by 2. It means that I'm just going to get 2 rows, 2 columns, which I'm going to have 4 elements there, which I put it as an empty box. I'm just going to find the empty boxes in there. The first element inside the resulting matrix, what is the address to that? It's located at row number 1, column 1. Why? Because look at that. I have column 1, column 2, row number 1, row number 2. Then the element, the first element there, ID is 1, 1, row 1, column 1. How to find it? I have to multiply the first column into the first row into the first column, right? Everything is the same. It becomes 1 over root of 3 times 1 plus 1 over square root of 3 times 1 plus 1 over square root of 3 times 1. Everything is the same. Then you get 3 over square root of 3. How about this one? The element here is 1, 2, located at row number 1, column number 2. Then what is column number 1? Row number 1 is this. Column number 2 is this. Exactly. It becomes 0. Guys. Brilliant, brother. Guys. Excellent. Now, look at this. This becomes 1 over root of 3. 0 times 1 is going to become 0. Minus 1 over root of 3 becomes minus 1. Then I get 0. Brilliant. 0. The other element, which we have 2 by 2. Huh? 2, 1. 2, 1. Okay. Look at that. It becomes 2 by, this is row number 2, column number 1, which becomes what? 0. Let me see, double check. Becomes row number 2, column number 1. It becomes this. Who said 0? Kajal. Brilliant. 0. We got 0. Now, the other element, this is 2 by 2. Let me, guys, look at that. Show all the talents. Brilliant. Now, this one, row number 2, column number 2. We have square root of 1 over 2. We have minus 1 over square root of number 2 times minus 1 becomes plus 1. Then, as you said, becomes 2 over, let's go 2. Guys, for you all yourself, great job, everyone. Great job. Now, then the final thing that we are just going to do. What did we start? Then this is this matrix that we got. It's by accident that we just got the upper triangle 0, but it happened here. Now, then what did we do? We said that we are just going to start by the matrix. This is the final point. I hope that you all write it because this is the final 2 minutes of the session. We said the matrix, a given matrix A. A given matrix A can be a given matrix of the gene expression of a cancerous tumor. Now, we factorize it. We decompose that into 2 matrices Q and R. With the condition we set forth that Q is orthogonal. You saw we benefited from that because the inverse of it was its own transpose. And R, which is the upper triangle matrix. We just started by that. Now, then what we did was, I gave you an example A matrix as plus 1, plus 1, plus 1, plus 1, 0, minus 1. Then we saw that this matrix can be decomposed into 2 matrices. The first matrix, this is the given matrix A. The first matrix was Q, was 1 over square root of 3, 1 over square root of 3, 1 over the square root of 3 plus 1 over the square root of 2, 0 minus 1 over the square root of 2 times a 2 by 2 matrix, 3 over the square root of 3, 0, 0, 2 times over square root of 2, which essentially, what is that? This is matrix A, which we were given. This was matrix Q, which we just find it by the projections and normalization. And this matrix is the upper triangle matrix R that we find there. Then all the things that we did today was a very important method. After last week, we talked about the singular value decomposition. It was tremendously important. This week, we talked about another decomposition method that was an orthogonal matrix times an upper triangle matrix. Now, I'm just going to finish the session by having you a very quick assignment to do. Then so far, what we learned was that we learned two methods last week. The singular value decomposition, we talked about that. And today, we talked about QR. This is called QR decomposition. Then by now, you have two methods to decompose a given matrix. Singular value decomposition and QR decomposition, two methods. Then the question which I'm just going to ask you is this. And you have to just answer that part of the submission that you're just going to do. If you are given a matrix which it shows the gene expressions from a cancerous tumor, for example, you have, for example, by the biopsy, you have extracted a part of, I should say, for example, the tumor cell, you sequence that using the alumni methods, you form a matrix. For example, you have a given gene, you have the counts for it. You form a matrix by that, the gene expression. If you decompose that by either these two methods, singular value and QR, what is the interpretation of each decomposing matrix that you have done? For example, if you have the gene expression, what the matrix of the single value of the tumor means. Or if you use the QR methods, what is the orthogonal Q matrix of the gene expression of the tumor means? Then please write it as a format, okay, in just one page. What is your understanding of it? And submit it by next year. No, sorry, by next week. Okay, I'm just going to stop the show. Any questions so far? Happy? I'm going to stop.